Hello everyone, I am Jaeyoung Lee and welcome to my talk on the work Benchmarking Video Object Detection Systems on Embedded Devices under Resource Contention. This work is jointly done with Pongchong, Ran, Noah, Venkat, Professor Lee, Professor Bakchi, and Professor Chatterjee. We are a group from Purdue University, University of Wisconsin-Madison, and the Army Research Lab. As technology advances, applications of video object detection tasks in the real world are increasing in demand, and one such example would be a self-driving car. A video object detection differs from an image object detection task, where there are some levels of continuous content among input frames. Also, as seen from the video, there could be latency requirements for real-world applications, which in this case would be detecting people and cars in a timely manner. From here comes the motivation of our work. Mobile video object detection tasks, like self-driving cars, can benefit from the advantages of edge devices. Edge devices are portable, energy efficient compared to a server-class machine, and comes at a low cost. However, they do come with drawbacks. They have limited computation resources such as GPU, CPU, and memory. Also, the portability comes with a cost of limited power source. Such limitations impact real-world applications where latency is a critical factor. Furthermore, there could be coexisting applications along the detection task where the latency would increase even more. There have been many approaches to address these limitations in resources of edge devices. One approach is designing the network model backbone to be more efficient. First, here are some examples of human-designed efficient components to reduce the network size and computation cost. For example, GhostNet designed a Ghost module to efficiently reuse features, and MobileNet v2 uses inverted residual blocks to reduce memory and computation cost. Another emerging field is to use the neural architecture search technique to find the most efficient design of the network. MNASNet and FBNet are examples of recent studies that use this technique. A more systems-driven approach to create an efficient pipeline is to design an adaptive network that could adapt to different scenarios. AdaScale proposes a scale regressor to adaptively scale the image for better accuracy and speed, and BranchNet proposes a network with early exits that could save computation cost based on the confidence of the detection in the early stage of the network. Most of the existing works focus on the accuracy and latency of a detection model. However, for an edge device, resource constraints for computation and energy should also be considered. We define the computation constraints as contention, where some examples would be sensors or other applications running along the edge device that shares the resources with the detection model. We experiment with different models, different environments, which would be different edge devices, and different contention levels to investigate the accuracy, latency, and energy consumption for each scenario. Let's first start with the models. We propose an adaptive model, FastAdapt, that is based on our previous work, ProxDet. FastAdapt is a highly adaptive detection pipeline that could adapt to the available resources and contention. If you see the figure on the right, a typical detection framework would have an input, then process the input through a deep neural network, and then get the detection results as an output. Here, we first add an object tracker to the framework. A tracker could keep track of the detections generated by the detector and save GPU resources by substituting the detector for a certain amount of frames. So, we do detection followed by several frames of tracking. This is possible as videos has similarity in content for neighboring frames. Next is our design of tuning knobs. For the detector, we introduce the input shape and number of proposals as tuning knobs, where the input shape knob controls the size of the image that is fed into the detector, and the number of proposals knob controls the number of proposals of object region candidates. Then comes the tuning knobs for the tracker. Tracker type controls different tracker types used, such as median flow, KCF, and CSRT tracker. The downsampling ratio controls the downsampling rate of the image fed into the tracker, and the sampling interval controls how often the detector will be triggered. For example, if the sampling interval is 8, the detector will be triggered every 8 frames, and the tracker will track the detected objects for the other frames. Last will be the scheduler. The scheduler chooses the optimal configuration to match the given latency requirement or resource budget. We implemented 2 additional baselines by adding a simple version of our adaptive features. FastRCNN Plus, which will be called FRCNN Plus, and YOLO Plus are the 2 implementations over FastRCNN and YOLO respectively. These 2 models has the scheduler and 2 tracker tuning knobs removed, which are tracker type and downsampling ratio. We experiment with different combinations from the pre-selected tuning knob sets, as there is no scheduler to control this, and present the results with data points on the Pareto frontier. FRCNN Plus has 2 tuning knobs, input shape, and number of proposals. YOLO Plus, on the other hand, has only the input shape knob due to the fact of not having a region proposal network. In addition, we experimented with state-of-the-art video object detection solutions to further explore the impact of contention. We selected the state-of-the-art models based on the following 3 guidelines. First, the code has to be open-sourced. Second, the pre-trained weights trained on the ILS VRC 2015 VIT dataset is available. And lastly, the model does not crash or hang on our lowest computation device, which is the Jetson TX2 board. The selected models are as follows. First, SILSA with ResNet 50 and ResNet 101 as the feature extractor. Next is Mega's base model with ResNet 50 as the feature extractor. Next is REPP with YOLO v3 as the feature extractor. And last, YOLO v3 base model from REPP provided by the authors. Here are the embedded devices that we experiment with, which are Jetson TX2, Xavier NX, and AGX Xavier. 3 different devices with different computation powers are selected to observe contention and model performance under different conditions. The AGX Xavier is the most powerful board, and the Jetson TX2 board is the least powerful board. We propose a synthetic contention generator that generates computation on GPU. The contention generator simulates the behavior of collocated applications that may exist in real-world scenarios that could consume GPU resources. We run increasing CUDA workloads on the GPU till the GPU utilization hits 100%, and then selected 12 discrete contention levels that would give us the desired amount of GPU contention. We have focused on the GPU utilization as the selected models are heavyweight and are GPU-centric algorithms. For evaluating accuracy and latency, all 3 embedded devices were used and were fixed to the maximum frequency for GPU and CPU, disabling the DVFS feature for reproducibility. DVFS, which is dynamic voltage and frequency scaling, automatically controls the frequency of the processors and could cause inconsistent results under contention. The accuracy was measured on the full ILS VRC 2015 VIT validation dataset, which contains 555 video snippets with a total of 170K frames. We used the common metric of mean average precision for accuracy. The latency was measured on a randomly selected video with enough frames for average latency per frame, which had 828 frames. The latency on the first frame was excluded due to the large initialization overhead being included. The energy consumption was measured on the Xavier NX board with 3 power modes. The 3 power modes were selected as the ones that had the largest difference between them. We used the native API provided called TegraStats to measure the instantaneous power and calculated the energy consumption for the time duration of the inference task on each model. We used same selected video from the latency experiments with 828 frames. Here, we start with the results from adaptive models first on the TX2 board. FastAdapt shows best performance for both accuracy and latency, and is able to match the latency requirements. Compared to 0% contention, at 50% contention, FastAdapt's accuracy drop is 7.8% for 30 frames per second speed, and 1% for 100 frames per second speed. In contrast, FRCNN Plus and YOLO Plus are 1.5 times to 2 times slower with 50% and 90% contention. This is mostly due to more tuning options that FastAdapt has over different baselines. Still, FRCNN Plus and YOLO Plus were able to show adaptive performance with the trade-off between accuracy and latency, holding latency under 100 milliseconds over 90% contention level. FRCNN and YOLO do not have any adaptive feature and have a single data point, whose latency increases up to 1 to 2 seconds per image as contention level rises. For performance on Xavier NX and AGX Xavier boards, similar trend is observed. One thing to note is that even if we use more powerful boards, FRCNN and YOLO still suffers over twice the increase in latency at 50% contention. FastAdapt achieves 49.3% accuracy with 59 milliseconds per frame, which is about 17 frames per second, and the accuracy drops to 43.9%, running at 35 frames per second. FRCNN Plus is comparable to or even better than FastAdapt when the latency budget is sufficient. However, the accuracy drops quickly when the latency budget decreases to 33 frames per second. YOLO Plus has an accuracy at 44.2% when latency budget is 20 frames per second. Also, we observed that over 50% contention level, the contention is saturated. We believe that this is due to the fact that the contention level is calibrated under the condition where the contention generator is the only running application. Under real-time environments, the OS scheduler may interfere to prevent the contention generator from drawing more resources while running along with the detection model. Next are the state-of-the-art baseline models' accuracy and latency performance under contention. The accuracy ranges from 51.25% to up to 81.5% as follows. Results on Jetson TX2 board and Xavier NX boards shows similar trend of increasing latency with increasing contention level for all models. Also, the contention saturation mentioned from the previous slide is also observed with these models, where 50% contention and 90% contention latency is very similar. Most models were observed to run over 250 milliseconds even with the AGX Xavier board, which may not be sufficient for real-time inference. One point to note is that RAPP plus YOLO v3 model achieved significant accuracy of 74.81% MAP with relatively low accuracy. Even with the most powerful board, the latency is increased more than 2 times under GPU contention over 50%, and this shows that resource constraints or multiple apps sharing resources impacts the latency performance of a model. The last part is the energy consumption experiments. We first present the instantaneous power measured for a total of 9 models, excluding the YOLO v3 baseline from REPP, as the additional time introduced by REPP was too short to differentiate the two baselines. All instantaneous power is measured by the TegraStats API provided by the board. The main impact of using different power mode on models is shown with the maximum power on each plot, which matches the power budget for each mode. To investigate further, each power mode comes with a different number of CPU cores, different maximum frequency for CPU, GPU, and the deep learning accelerator. Mode 0 and 2 has almost similar plots and results, as their specifications were similar, but Mode 0 was always faster to Mode 0, implying that the CPU frequency could have a bigger impact than the online CPU cores. Mode 4, on the other hand, has longer inference time with lower max power due to the lower power budget and limited frequency for all CPU, GPU, and the deep learning accelerator. FRCN Plus and YOLO Plus has 50% and 80% reduced latency compared to its respective original model. Also, FastAdapt, FRCNN Plus, and YOLO Plus has a much lower total inference time and has a more dynamic and fluctuating plot, which could be due to the tracker and adaptive features that does not use GPU intensively. Based on the instantaneous power, we calculated the energy consumption. Results shows that even if Power Mode 4 has the longest inference time, the total energy consumption is lower by 10% compared to Mode 2 and Mode 0. Total energy consumption is higher for Mode 2 compared to Mode 0, possibly due to having more CPU cores online. FastAdapt, FRCNN Plus, and YOLO Plus has the lowest average total energy consumption, around 2,200 joules, and FRCNN Plus and YOLO Plus is reduced more than 60% in energy consumption from its respective original model. This shows that our addition of tuning knobs and tracker is effective not only latency-wise, but also energy-wise. From our sets of benchmark experiments, we conclude that contention truly plays an important role in latency performance on edge devices. Latency performance is impacted for all boards and models under contention, increasing the latency up to 2 times larger. Also, the impact is bigger for smaller available resources, such as when using a less powerful board. This suggests that adaptive features are needed to ensure performance on edge devices with latency requirements. Energy experiments on the edge devices show the impact of different power modes on the model. Our implementation with tracker and tuning knobs results in a larger reduction of energy consumption. In addition, deeper feature extractor uses more energy. For example, SOTA with ResNet 101 as the feature extractor has 20% higher energy consumption compared to SOTA with ResNet 50 as the feature extractor. Thank you for listening. This work is funded by National Science Foundation, Army Research Lab, National Institute of Food and Agriculture, and Adobe Research. If you have any questions, please contact us through email, website, or Twitter. Thank you.